Good afternoon, everybody. I apologize that I am not able to be there, but I'm very, very thankful that Miss Barabo is standing in for me, and she'll be able to answer some questions that you guys might have. The plan for this week, just to kind of lay things out in the next week, because I think the end of next week kind of marks a break, we'll be passing out a calendar. It's an updated lecture schedule because of the snow day last week. But basically this week we're going to cover section 3.4, and then Wednesday and Thursday we're going to cover section 3.5. And then next week our exams, so we're going to spend Monday doing some review and answering any homework questions you might have. And then I believe our exam is on Thursday morning from 8 to 10. So this week, we'll also be passing out the schedule of things that are due. Should look like this. This week, you've got 2 homework assignments that are due, and then on Thursday, we've got a quiz. I'm going to be flexible about turning in that homework this week because last week was kind of weird because you weren't supposed to have homework over the Christmas break. But then we had a snow day, and it's kind of all... So you'll see on the sheet that's passed out that Monday is supposed to have... So today there's supposed to be a homework due on section 3.2, mean value theorem problems. If you don't have those done today, you can turn those in on Wednesday. It's okay. You can turn them in either today or Wednesday. And then Wednesday, you'll see a homework that's assigned, section 3.3, which is our increasing, decreasing stuff, which I'll review in a second. And then concavity stuff that we're going to cover today. That you can do on Wednesday. You can turn that in on Wednesday. If you want to turn it in on Thursday, that's fine too. It's not super intensive. You should be able to get it done by Wednesday. If you've got any questions or issues, you can ask Ms. Barabo, you can ask me. Either one of us is perfectly fine. And then the quiz on Thursday is going to cover section 3.1 through section 3.4. And I'll, when we get to Wednesday, I'll give a little bit more of an overview about what the type of thing that you're going to see on that quiz. So I know that 4 sections is kind of a lot of material to have one quiz over. I'll narrow that down a little bit when we get there. Okay? So let me just review here kind of what we talked about previously. So section 3.3 was on increasing and decreasing functions and finding local maxes and mins. Okay. And the idea here was that, again, a function's increasing basically if it's going up, it's decreasing if it's going down. Okay, we gave a technical definition, but in essence, a function's increasing if it's going up, it's decreasing if it's going down. And one thing that we notice is that there's a relationship between increasing and the first derivative, which is maybe a pretty obvious relationship. But over here, the derivatives at points, if the function has a derivative, the derivatives are positive, the slope is up. Over here, the derivatives are negative, the slope is down. So if somebody asks you, where is a function increasing, where is it decreasing, and all you have is the formula, what you can do is you can take the derivative, and the places where the derivative is positive, that means that the original function is increasing. Okay, the places where the derivative is negative are places where the function is decreasing. Okay, so, and the thing that we saw on Wednesday when we talked about this is the way that you figure out where the derivative is positive or where the derivative is negative is we first find where the derivative equals 0 or does not exist. And then we draw a number line. Let's say at 0 and at 2, the derivative is 0. Then what we do is we test points around in the derivative. So I might, for instance, take the number 1 and plug it into the derivative to see if the derivative is positive or negative. I might take a 4, something that's bigger than 2, and plug that into the derivative and see if that's positive or negative. I might take something else like -2 and plug that into the derivative, see if that's positive or negative. The places where the derivative is negative, the function is decreasing. The places where the derivative is positive, the function is increasing. And so then this gives me a picture of where my local maxes and mins are. So if my function is going down, then the slope is 0, and then it's going up, then what's happening right there is I have a local min. So one of the other things that we saw is that if you're looking at the derivative, and the derivative of a function goes from positive to 0 to negative, then you've got a local max there. If it goes from negative to 0 to positive, then you've got a local min. Okay. If it does something else, like, for instance, if it goes positive and positive, then what's happening is you've got something kind of like an x cubed, and there's nothing going on here. It's not a local max, it's not a local min. Okay, so it has to change. It has to change from being positive to negative or negative to positive. The other thing to watch out for here is that the function actually has to be continuous. So you can't, for instance, if this was my function, make sure you guys can see that. If at 2, my function went like this, and then like this, it's increasing. If I didn't actually know this and I did something with the formula, and then at 2, before 2 the derivative was positive, and after 2 it was negative, I might be tempted to say that 2 is a local max. But 2 is not a local max because it's not even continuous there. It doesn't actually achieve a maximum value there. So just be careful that if the derivative doesn't exist, and you're looking at local maxes, it could not exist because it looks like this, which is great. That's totally fine. That is a local max. Or it could look like this, and that's bad. So you just kind of need to watch and see what's going on there. So your homework in section 3.3, I think I've got about 6 questions there. And that's just dealing with, you've got a formula, and you're asked, find the critical numbers. That's where the derivative is 0 or does not exist. It's your critical numbers. And then draw your number line and test points around to see where the derivative is positive or negative. And from that, figure out where's the function increasing or decreasing. Where are your local maxes and mins? Okay, so that's what we went over on Wednesday of last week, which already feels like, I know, quite a ways away. All right. So let's move now to the next section. Okay, this is section 3.4 on the topic of concavity. Okay, not cavity like a cavity in your tooth. Concavity, concave. This comes from the word concave. And the idea here, concavity actually has to do, concavity is kind of another word for curvature. It has to do with how a function is curved. Okay, so we're going to talk about this conceptually, then I'll give you a little more rigorous definition here. So sometimes you'll see a function that's curved up, or you might see a function that's curved down. Okay? When a function is curved up like this, you see the curvature is going up. We're going to call this is not a precise definition right now, but we're going to call this concave up. If you're curved up, we may abbreviate this CU. And then over here, we're going to call this concave down. And I might abbreviate this CD. Okay, so one of these is concave up, the other one is concave down. All right. One thing I want you to notice here is that concavity, the curvature, is totally independent from the from increasing or decreasing. So for instance, here you notice I'm concave down. Part of this is increasing, part of it's decreasing. So the fact that I could be increasing and concave down, curve down, or I could be decreasing and curved down. Notice over here I can be decreasing and curved up, or I can be increasing and curved up. So increasing, decreasing is related to concavity, but you can have increasing or decreasing and concave up or down. You can have either kind of collection, either pairing of those. So so those can happen. So now to get us a little bit more precise definition, one thing I want you to notice, we're going to draw in some sort of mini tangent lines. We're going to look at slopes. Okay, slopes of tangent lines should immediately set off your radar and say we're looking at derivatives. Okay, so we're going to look at some slopes here. So let's draw in some. I don't know if you can see that or not, but I'll trace it with my hand too here. Here's a derivative. So the derivative is negative, kind of close to zero, ends up positive, more positive, more positive. So one thing that I want you to notice here is that the derivative, the slope of the tangent line, is getting bigger. In other words, the derivative is increasing over here. Whereas over here, the derivative started off kind of positive, ended up zero, and then went more and more and more negative. So when you're curved down, the derivative is decreasing. And this is actually the more precise definition of being curved up and curved down. Conceptually, curved up just means, concave up just means curved up, concave down just means curved down. But the formal definition it has to do with the derivative. And so we need, let's let f be differentiable on some open interval. Okay, and then we say f is concave up, remember that means curved up, on that interval if the derivative is increasing on the interval. Okay, so the derivative, the slopes are increasing. That's what this is the definition of being concave up, curved up. And the definition of being curved down, concave down on the interval is if the derivative is decreasing. Okay, so we're curved up if the derivative is increasing. We're curved down if the derivative is decreasing. Okay. Now what I just reviewed, the fact that I'm talking about increasing and decreasing should also remind you of a derivative. So what this leads us to is so what we'd like is a simple way, just like what I just presented before. If I give you some formula and I said, where's the function increasing and decreasing, you should know now how to do that. I take the derivative, I find where the derivative is zero or doesn't exist, and then I test points around to see where the derivative is positive or negative, and that's going to tell me increasing or decreasing. Okay, pretty simple. Now, taking the derivative is not always simple, but that's a pretty simple method for finding increasing and decreasing. We'd like a similar simple method for finding where is a function curved up, where is a function curved down, okay? So that's our goal, and so I'm going to stick the goal here let's say I want to know where is a function concave up. That's my goal. Now what we just said is that that means that the derivative is increasing. Okay. Now here's where we have to put on our thinking cap for a second. A function is increasing. So I'm going to put this thing in blue, just so you can kind of you're gonna have to think outside your brain just for a second. A function is increasing if its derivative is positive. Okay, think about that again. A function is increasing if its derivative is positive. Now in this case, we want this blue function to be increasing, so we want its derivative to be positive. Okay, the derivative needs to be this function f prime needs to be increasing, so we want its derivative to be positive. But that is exactly the second derivative of the function. So what happens here, just like the first derivative, what we were talking about before, the first derivative is related to increasing and decreasing. Turns out the second derivative is related to curvature, concave up and concave down. So similarly, if I want to know where is a function concave down, that's where, by definition, the derivative of f is decreasing. But that derivative of f, if I think of that as a function, that function is decreasing if that function's derivative, it's decreasing if that function's derivative is negative, and that means that the second derivative of f is negative. Okay. So we call this is just kind of unwinding some definitions that we've talked about before, but we call this the test for concavity. Okay, so so if I say, where is a function concave up, where is it curved up, where is it curved down, all you do is, just like we did with the first derivative, you look at the second derivative, okay? All right, so if f has a second derivative on an interval, but sometimes these functions don't have second derivatives. Okay, we haven't looked at really weird examples, but the places where the second derivative is positive means that the function is curved up. The places where the second derivative is negative means that the function is curved down. Okay. That makes sense? So we look at the second derivative. Basically, you find, just like we did before, you find the places where the second derivative is 0 or does not exist. You draw a number line. You mark those places where it's either 0 or does not exist for the second derivative. And then you test points around in the second derivative to see about concavity. And so if the second derivative is positive, it's concave up. If it's negative, then it's concave down, it's curved down. Now the mnemonic, the way that people memorize this or remember this, there's a lot of different ways that people do remember this, but one that I've seen that is really catchy and I think it's easy for people to remember is that if the second derivative is positive, the function's curved up. If the second derivative is negative, then the function's curved down. Okay, that's one easy way to remember concavity. Okay, so what we're going to do now is we're just going to look at we're going to look at a few examples of computing where is a function concave up, where is a function concave down. Okay, so let's take a look at, for example, let's pull out the function x cubed minus 27x. All right, so x cubed minus 27x, and I'm giving this function, and I would say, for example, I could say, where is this function increasing or decreasing? And you could do some work there. In fact, let's go ahead and just do that. Why don't we go ahead and just review that with this example here. So let's start with, where is this function increasing or decreasing? Okay? We're just going to start with that. And that means we're looking at the first derivative. So the first thing we do is we look at the first derivative. So in this case, the first derivative is 3x squared minus 27. All right? And that, there's no place where that does not exist. Remember, we're looking for critical numbers here. There's no place where that does not exist. When I set it equal to 0, I can factor out a 3. And I get x squared minus 9, and that factors as x minus 3 and x plus 3. Right? So this thing is 0 at 3 and negative 3. So I'm going to fill in here on my number line. The derivative is 0 at 3 and negative 3. And so now, in my derivative, I'm going to test some points around this, around 3 and negative 3. Remember, we're testing the derivative, not the original function. Okay, so if I were to plug in 0 in the derivative, I would get negative 27. That's a really big negative number. If I pick something to the right here, if I were to pick 4 squared, well, let's pick something huge because that'll make it easy. If I pick 10, this is really big, it's 300. So I'm definitely going to get a positive number there. If I picked down here some big number like negative 10, when I square that, this is still 300. So this is still a big positive number. We just need to test one point in each of these areas. And in these places where the derivative is positive, the original function is increasing. In the places where the derivative is negative, the original function is decreasing. So you can also see here, so this function is f is increasing on the interval from negative infinity to negative 3 and from 3 to infinity. F is decreasing on the interval from negative 3 to 3. Okay? So if we wanted to, we could actually take negative 3 and 3 and plug them into the original function. And what we should find is that we get a point here and a point here, and it's going up to this point, down to this point, and then up after that. Which means the other thing, besides increasing and decreasing, that this immediately tells us is that we have a local min, max, or nothing here. That's going to be a max, a local max at x equals negative 3, and a local min at x equals 3. Okay? So that's our increasing, decreasing, local maxes and mins. That all has to do with the first derivative. Make sense? So now what we're going to do is we're going to look at the second derivative and see what's going on with our curvature. Are we curved up or down, and where? Okay. So let's look at concavity here. So we're going to take a look at the second derivative, which means that I'm going to take the derivative of this thing, this first derivative here. Okay, so the derivative of 3x squared, we leave the 3 alone. Derivative of x squared is 2x to the 1. And then the derivative of 27 is just 0. So our second derivative is just 6x. And again, I asked two questions. Where does this not exist, or where does it equal 0? There's no problem with the dn, with does not exist. It equals 0 when x equals 0. So if I'm looking at the second derivative now, at 0, the second derivative is 0. Here's the second derivative, simplified right there. So if we pick something to the right of 0, like 1, this is going to be positive. If we pick something to the left of 0, like -2, this is going to be negative. Now remember, this is the second derivative. So if the second derivative is negative, the function is curved down. If the second derivative is positive, it's curved up. So what we see here is that we're concave up on the interval from 0 to infinity, and we're concave down on the interval from -infinity to 0. So we're concave up here, concave down here. And that's consistent. If you think about what this thing looks like, it's probably going like this, and then it turns around and it starts curving up. That point where it turns around and starts curving up has a special name, and I'll come back to that in a second, but I don't want to throw too much at you at once. Okay? So we're curved down to the left of 0, and we're curved up to the right of 0, and that has to do with the second derivative. All right? Any questions? Okay. I want to do one more example here. So I'm going to go ahead and erase everything. All right. So here's my next example here. And we have to make these functions a little more interesting, right? So here, yeah, I know what you're thinking. Sorry. All right, so what we're going to do is we're going to look at increasing and decreasing. And then once we do that, we're going to look at concavity. Okay, we're going to look at curvature. So let's start with increasing and decreasing. So let's take a derivative. So, yeah, and here comes the quotient rule. I know that you're not all that excited about that. All right. Okay, so we square the bottom. We have low, that's the bottom, d high. The top is not that complicated. So the derivative of the top is just 2x. Low d high minus high d low, and the derivative of the bottom is also just 2x. And then we square the bottom, and there you go. All right? So it looks bad. It's actually not quite that bad. Let's go ahead and simplify. So we've got, if we multiply the 2x out, we've got 2x cubed minus 2x. And if we multiply this in here, we've got minus 2x cubed minus 2x. Again, we've got the bottom squared. All right, and the 2x cubed minus 2x cubed actually cancel, and the other two end up combining. So we've got a 4x on the top minus 4x over x squared minus 1 squared. That's my first derivative. It might look bad. It's not too bad. All right, so let's we got to ask two questions like we've done before. Where does this not exist? And in this case, actually, we have to pay attention to that. So this does not exist when that denominator equals 0. The denominator equals 0 when x is 1 or x is negative 1. Make sure you catch both of those. Okay, so it does not exist when x is 1 or negative 1. The derivative equals 0 when remember, a fraction equals 0 if the top is 0. The only way the top of that fraction ever equals 0 is if x equals 0. Okay, so those are my critical numbers there. And so I'm going to draw my number line here with my derivative. And here the derivative is 0, and at 1 and negative 1, the derivative does not exist. Now, one thing I just want to point out here is that in the original function, it's not defined at 1 and negative 1. It actually kind of, if you look at it, you can probably guess you're looking at a vertical asymptote at both 1 and negative 1. So we're not going to get local maxes or mins here. It's just going to be a vertical asymptote there. Right? So now what we're going to do is we need to plug in points around and see what's going on here so that we can figure out what's happening in terms of increasing and decreasing. So let's pick something, let's start over here, let's pick something easy, let's pick 2. If we plug in 2, the top would be negative 8. One thing I want you to notice about the bottom though, the bottom is something squared, so the bottom will always be positive. So the only thing we really have to figure out is what's going on the top. So on the top, if we plugged in 2, we get negative 8. The bottom's positive, so negative over positive would give me a negative. Same thing if I plugged in something in here like a half. 4 times a half is 2. The top is negative 2. Again, the bottom squared is always positive, so negative over positive is negative. Back over here, if I pick negative 2 and plug that in, I'd be looking at negative 4 times negative 2. This is positive 8. Again, the bottom's always positive. Positive over positive is positive. And then the same thing's going to happen at negative 1/2. Negative 4 times negative 1/2 is positive 2. So I have positive on the top and bottom, I get positive overall. Okay? So what that means, if the derivative is positive, the original function is increasing. If the derivative is negative, the original function is decreasing. So what we have here is that the function is increasing on the interval from negative infinity to negative 1, and then negative 1 to 0. It's actually not increasing this entire way because it has that vertical asymptote, so it's actually going to end up jumping. So we have to list these as 2 separate intervals. And then it's decreasing on the interval from 0 to 1, and then 1 to infinity. Okay, it's decreasing on these. So what's actually going on is it's going like this, then it's going increasing, then decreasing, and then decreasing again. So what that also means is that we have a local max here, but no local min. So we have a local max, make sure you can see this, local max at x equals 0, and then there's no local min. Okay? Doesn't at any point do that. All right. Hopefully that's clear. And guess what we're going to do now? We're going to ask, where is this concave up or concave down? And in order to do that, we have to take the derivative of this fun thing right there. All right. So that's what we're going to do. Okay, so we're going to look at the second derivative now. All right. So we're going to go low. And remember, we're starting with this. Low d high. Okay, the derivative of the top is just negative 4. Minus high, negative 4x. D low. And in order to do the derivative of the bottom, we're going to have to use a rule. What rule will we need? We need the chain rule. So we're going to do derivative of the outer. So this is, the outer is x something squared. So we're going to do derivative of the outer. Plug in the inner. You guys can't really even see that, can you? I'll adjust here a little bit. All right. Derivative of the outer, plug in the inner, and then the derivative of the inner is just 2x. That's our low d high minus high d low. And then we got to square the bottom. So if it was squared before, now it's to the 4th power. There you go. All right. So one thing I want you to notice as when we're about to simplify here, one thing that I want you to notice is that I have something squared in this term, that same something in this term, and I have 4 of them down here. So what I'm going to effectively do is pull, I have an x squared minus 1 in both of these terms, so let's pull that x squared minus 1 out. I've got one of them left here. So I pulled one of the 2 out. This one's gone. I pulled it out. And the reason I'm doing that is that now I've got one of them up here and 4 of them down here, so I can cancel one of these and leave 3 of these down here. That's actually going to make our lives a lot easier here. Okay? Did you catch what I did? I pulled one of these out and then this one out. Imagine multiplying them back in. And then I got one of them here and 4 of them down here, so I canceled one and that left 3. So now we're just going to simplify this top. I've got minus 4x squared plus 4. And I've got 4 times 2 times 2 is 16, and negative times negative is positive, so I've got plus 16x squared. Okay. All right, and then we just, one more step. That's 16x squared minus 4x squared is 12x squared. So we've got the plus 4. All right. So that is our second derivative. Not too bad. Okay, so we're going to ask now to do concavity. We're going to ask the same questions we asked over here. Where does this not exist? And the place where it doesn't exist is the same issue that we had before. It does not exist when x is 1 or when x is negative 1. If I say where does this equal 0, a function's only 0 if the top is 0, but this is something squared plus 4. This can never be 0 or negative. So there's actually no place where the second derivative is 0. All right? So what we do now for this second derivative is we label where the second derivative doesn't exist and the original function doesn't exist there. And we're just going to test points around to see what's going on here. So let's pick a point. My favorite point is 0. If I plug that into the second derivative here, I get 4 on the top, and 0 minus 1, I get negative 1 cubed is negative 1. So 4 over negative 1, this is negative on the bottom. All right, if I pick something over here like 2, the top is definitely positive. And the bottom is also positive. 2 minus 1 is 1 cubed is 1. So it's positive there. If I pick negative 2, the same thing's going to happen. I'm going to be positive over here. So what's going on is we're curved up here and here, and we're curved down there in the middle. And this curved down part should actually make sense because remember, we were increasing over here and decreasing over here, which means that we probably should be curved down. These things are actually related to each other. So my function is concave up. It's curved up from negative infinity to negative 1, and then 1 to infinity. And it's curved down on the interval from negative 1. Okay, so that's my concavity. Right? Any questions? All right, let me go ahead and give you a 5-minute break here. You can go ahead and pause the video if you want 5 minutes, and then we will jump back in. Just go ahead and pause, and I'll erase here. Okay, you should be back now. Hopefully Hopefully it was just 5 minutes. Okay, one thing that I want to point out, I want to go back to, if you want to flip back in your notes for a second to the previous, one of the previous examples that I gave you here. X cubed minus 27x. What we had was, I'm going to skip the work that we did because you just saw me do it earlier. But remember, it was increasing, decreasing, and increasing when we were looking at the first derivative. And then when we were looking at the second derivative was 0 at 0, and it was negative to the left and positive to the right. So in other words, the function was curved down to the left of 0 and curved up to the right of 0. Okay, there's a special name if the function changes concavity at a place where the function actually is continuous. Okay, the function has to be continuous there. You can't have vertical asymptotes or weird things like that. But if the function is continuous at a place and it changes concavity, we're going to give that a name. We're going to call that an inflection point, a point of inflection. Okay. So a function has a point of inflection, okay, or inflection point. If the second derivative changes from positive to negative, or from negative to positive there, and f is continuous. Okay? So we're going to call that a point of inflection, an inflection point, when it changes from negative to positive or positive to negative, and the function's continuous there. Okay? So in other words, if we have, for instance, if it's curved down and then curved up, that point right there where we go from being curved down to curved up, this point is a point of inflection. Where the curvature changes. Okay, now there's two things that I want to point out that are super important about this. One of them I've kind of already emphasized, but the first one is that the function must be continuous there. You cannot have something like this. Okay, here it's curved down, here it's curved up, but that value is not a point of inflection. Okay, don't do that. Points of inflection have to actually be points on the graph. If they're not points on the graph, it's not a point of inflection. All right? The other thing that I want to point out is that it's called a point of inflection, and whenever we call something a point, it actually has to be an x comma y value. Okay, so a point, you will not say it has a point of inflection at x equals 0. We say that for local maxes and mins, and that's fine, but for points of inflection, you have to actually give the coordinates. So for example, here, if it changes concavity at x equals 0 from negative to positive, we have to take x equals 0, plug that back into the original function, and so the original function, 0, 0, 0, 0 is my point of inflection. You would not say this has a point of inflection at x equals 0. You would say it has a point of inflection at 0, comma 0. Now the mistake a lot of people make is they take x equals 0 and they plug it back into the second derivative or the first derivative rather than in the original function. So be super careful of that as well. Okay? So let's do one more example, and then there's just something that I want to point out about local maxes and mins, and then we'll actually be done for today. So let's erase this here. We're going to do one more example. I'm not going to run through all of the increasing and decreasing stuff on this one, but I want to ask the question. X to the fourth minus 4x cubed. I want to ask the question, where are the points of inflection and what does the concavity look like on this one? Okay, so x to the fourth minus 4x cubed. What does the concavity look like? What do the points of inflection look like? So let's take, in order to get the second derivative, we have to do the first, so let's do that. 4x cubed minus, the 4 stays there, the 3 comes down, so we end up with 12x squared as the first derivative. 4x cubed minus 12x squared. The second derivative, let's bring the 3 down, so we end up with 12x squared minus, here the 2 comes down, so we end up with 24x. Okay, again, we're not dealing with increasing, decreasing, so I'm not going to do anything with this first derivative, but I am interested in the second derivative. There are no issues here with does not exist. If I set this equal to 0, I can factor out a 12x, and I'm left with an x in the first part and a 2 in the second part. So this equals 0 at x equals 0 or x equals 2. That's the two places where this equals 0. So the derivative, the second derivative equals 0. Second derivative equals 0 at 0 and 2. And so now I'm going to just take some numbers around and plug them in. So if I plug in 1, for example, I'd get 12 minus 24, that's negative. If I plugged in, let's just plug in something big, 10, I get 1200 minus 240, so I get a really big positive number here. If I plug in negative 10, this is positive, and now this is also positive, so this is really, really positive. So if we're talking about derivatives, second derivatives, the original function is curved up when the second derivative is positive, and it's curved down when the second derivative is negative. So again, we're concave up on the interval from negative infinity to 0 and from 2 to infinity. And we're concave down from 0 to 2. And now it looks like we are continuous at these 2 points and change concavity there. So we have points of inflection. We have inflection points at, now remember, we will not say x equals 0 here. We'll say 0, comma, and we plug 0 in. When we plug 0 into the original function, we get 0. And then at 2, comma, we have to plug 2 into the original function. That's 16 minus 32 is actually negative 16. So these are my 2 inflection points. Those are the places where the function changes from being curved up to curving down, or from curving down to curving up. Okay? Got it? Okay. The last thing I just want to cover briefly is that you can actually use the second derivative to figure out if you have local maxes and mins. Now, this is, I don't generally recommend that students use this. It's good to know that you can do this, but there's a reason why it's not generally, this isn't the best way of doing finding local maxes and mins. The best way to find local maxes and mins is to take the first derivative, set it equal to 0, find out where it's increasing and decreasing, and then use that to figure out what's going on with the original function. So that's called the first derivative test. What we're going to do here is called the second derivative test, and it also tells you some about local maxes and mins, but there are some situations where it doesn't give you information. Like it just can't tell, and then you have to go back to the first derivative test anyway. So that's why generally the first derivative test is best. The method that we use for finding local maxes and mins before is the best way. But there's another way that you can do this. So this is called the second derivative test. Okay, we're basically using concavity to find local maxes and mins. All right. Okay, so what I want you to think about is if I have a place, let's call it C, and the first derivative is 0 there, and the second derivative is positive. So in other words, I have a function, I have this place on the graph where the function is flat there, that's with the derivative being 0. It levels out, but the curvature is up. So in other words, it's curved up right there. So it's flat but curved up. What's going on right there? That's a local min, right? So if you know the curvature, it can actually tell you if you've zeroed out in terms of your slope, but you're curved up, then you've got a local min. If you've zeroed out there in terms of your slope and you have a negative curvature, okay, so you're curved down, then we have to have what there? A local max. All right. Here's the bad part about the second derivative test. If the first derivative is 0 there and the second derivative is 0, so it's not positive and not negative, it's actually 0 there, you can't tell at all what's happening. It could be a local max, it could be a local min, it could be nothing. For example, I'll just give you kind of a couple easy examples here. So if I look at x cubed, the derivative is 3x squared, and the second derivative is 6x. The derivative is 0 here at x equals 0, and the second derivative is 0 at x equals 0. But that's not a local max or min. But the same thing actually happens at x to the 4th, which actually is a local min. The first derivative is 0 at x equals 0, and the second derivative is 0 at x equals 0. So, sorry, you can't even see what I'm writing over there. But the point is that it's possible to have a local max or min, and this situation's happening. It's possible to have nothing in this situation is happening. So generally, it's better to figure out if you have local maxes or mins. You've already figured out if the derivative is 0 somewhere. You might as well just figure out if it's increasing around it, rather than trying to get, figure out like second derivative and then trying to plug the point in and that kind of thing. Okay. Well, let me just show you. I'll just show you what this looks like in an application like. Let me give you. Let's take just a slightly different example. This problem I just erased is actually a situation where this happens. So if you're curious to see another example of where this might happen, you can take a look at that problem that I just erased. But let me just do one more example and we'll be done here, and you guys can start on the homework if you've got some extra time. Okay, if I take the function x cubed minus 3x squared, and let's just look at the first derivative. The first derivative is going to be 3x squared minus 6x. Again, there are no issues where this does not exist. If I set it equal to 0 and factor out a 3x, what I'm left with is x minus 2 in the other part. Okay. So that now means that x equals 0 and x equals 2 are my critical points. They're places where the derivative actually equals 0. Now what this test is saying, what we would normally do is draw the number line, set the first derivative equal to 0 at 0 and 2, and then test points around to figure out local maxes and mins. What this test is saying is instead of doing that, what we're going to do is take another derivative. Okay, here's my first derivative. So if I take another derivative, I get 6x minus 6. And then if I plug in x equals 0 into this second derivative, you'll notice that the second derivative at 0 is -6. It's negative. So in other words, at 0, the first derivative is 0, and the second derivative is negative. It's negative curvature. So that means at x equals 0, I have a local max. Got that? The first derivative was 0. That means it's flat. And then the second derivative is negative. So that means that I'm curved down. So that means this is a local max here. At x equals 2, if I plug that into the second derivative, that gives me 12 minus 6 is 6. That's positive, so I'm flat but curved up. That means that x equals 2 is going to be a local min. This is a local max. Got it? So that's how the second derivative test works. But again, for the most part, I'm actually never on an exam going to tell you have to use one or the other. I normally would not figure out local maxes and mins this way. I would figure it out the normal way, just using the first derivative and then drawing a number line, testing points, and seeing where is it increasing, decreasing. That's the normal way, but this method also works. Okay? So if you've got some extra time, go ahead and utilize that to work on some homework problems. Again, there's a little bit of flexibility in terms of when that homework is due this week. If you've got questions, feel free to ask Ms. Barabo. Feel free to send them to me. Thanks so much. Have a great day.